Hey, welcome guys. This is my second video about proof the Dirichlet theorem of arithmetic progressions. If you haven't seen my previous video, that you can check it. Okay, so the final results of the previous one is that we introduced a Dirichlet character, and we proved the two theorem that if let's say if chi is not principal, that the partial sum is bounded. And if the chi is a principal one, that the partial sum is the order x. Okay. Okay. So now one immediately get a following about the Dirichlet series. Okay. So recall that if your partial sum is that big O of x theta, and then your Dirichlet series will converge, will absolutely converge when your real s greater than theta. Okay. Or theta should be greater than 0. Okay. Okay. And also if you're this is what I proved in the maybe a little bit long ago, but you can check out my previous list. If your partial sum is, let's say, a x alpha plus O of theta, alpha greater than theta, then your Dirichlet series will be a of s minus alpha. Okay, and the least term is the analytic part. Okay. Okay, so if one have this, then one immediately get the following, right? Because now we have a Dirichlet chi of the x, chi of x. Sorry, this is the partial sum. We get if chi is non-principal, that we get O of 1. Okay, so maybe depend on q, but let's forget about this. And the phi of q divided by q plus x plus OQ of 1 if chi is a principal. Okay, so now let's go to the proof. Okay, so now let me just highlight every detail and every step by step, and then finally we will our final results will depend on there's a very difficult lemma that I will prove in the final video. Okay, so let's consider three functions. Well, the first one is called SAQ. X defined to be 1 over P, where P is A mod Q. So A mod Q or prime. Okay, so this is the first one, and the P is less or equal to X. Okay, and the second is called FAQ, which is S. Okay, so sorry, sometimes I use Q looks like the G, but yeah, so you know every time I always write Q. Okay, I always use Q. Okay, so it's P, and the P is A mod Q, and then you do that 1 over P to S. Okay, definitely is theta. The real part of S, that defined to be sigma greater than 1. On the chi of the character is chi of P. This is the Dirichlet series. Chi of P. But only consider prime power. Okay, so and the sigma greater than 1. Okay, so our main theorem that I'm gonna to prove in this and the next video is that we want to prove that there are infinite A mod Q prime, right? So what we're gonna to prove is that we need to find the order of this SAQ. So the theorem is that SAQ of x is actually 1 over phi of q log x plus OQ1. Okay, so in this case, every big O notation that I write will depend on Q. Okay. Okay. Right. So this is what our goal. Okay. So and this goal is difficult to prove. So our goal is we need to relate this guy to this guy, and then relate this guy to this guy. Okay. And the final reduce to L function. So this is like maybe if you're familiar with computer science, that is somewhat like a reduction step, right? So you start from you want to prove that this guy is very difficult. This guy is difficult, and so you want to relate it to be something simpler. Maybe this guy is hard to simple to control, and this guy is control. Okay, so okay, so first the claim 1. The claim one is that this guy, this SAQ form, this SAQ form can be reduced from this FAQ sigma. Let's say this guy is 1 over phi of Q log 1 over sigma minus 1 plus O of 1. Okay, so I want to claim that actually this theorem that's come from some previous, it's come from this one. Okay, so let's prove this. Proof. So let's take sigma to be sigma x to be, let's say 1 over 1 plus 1 divided by log x. Okay, so this term will be this FAQ of sigma will be 1 over phi of Q log x, right? So let's do this and plus O1. Okay, so okay, so it looks like this FAQ is at most is the same as SAQ, right? Right. But in order to prove this, you need to show that their difference is at most of 1. Okay, because now these two functions looks very similar. Okay, if I take this s to be let's say take a real but with some x, then which looks very close to this. Okay, so our goal is to let's compute the difference between these two functions. Okay, so let's consider AQX minus FAQX. Okay. So this guy is P less equal to X, and the P is A mod Q. P1 minus sigma X divided by P minus P greater than X. P equals A mod Q. 1 over P sigma X. This guy is this, right? And then this guy is this. Okay. And their difference is just that I pick out 1 over minus x come from here and then pull out here. Okay, so this is this. Okay, so let's call this sigma 1. Let's call this sigma 2. Let's call it edit minus 1. Okay, so let's say compute a sigma of 1 sum. Okay, so sigma of 1 sum is simple, right? Because 1 minus P1 minus sigma x is could be written as 1 minus exponential log P log x. Okay, so this is less, very, very less to log P log x. If that P less or equal to x. Okay. And then this will make it sigma 1 less or equal to 1 over log x. Okay, right, log P. And the P, and do the summation, let's say P less or equal to x. Okay, so now you get 1 over log x. Log P less or equal to x. So what? So how do you do this control, right? So we have the prime number theorem, right? So you can try to bound this guy, but okay. So let me just tell you the results. Okay, so this is less or equal to 1. Okay, so this is by Merton's estimate. This is I talked this in the prime number theorem section that you can prove this by using prime number theorem, right? You only need, so basically some log P can be viewed as a 1 over x. Let's say log n times n and log n. Okay, you can try to do this integral compared to this, and then you get a 0. Okay, you get these guys can be arbitrary small. Okay. Okay, so let's consider sigma 2. So sigma 2 is this which is 1 over P sigma x, P greater than x. Okay, so you can try to prove this by using the Chebyshev bounds. Oh, but I guess you don't need to do this, right? Because sigma, you know that the P series results, right? So you know that if sigma x greater than 1, the summation 1 over P to the sigma x will converge, right? So if you take x to be large enough, then this guy will less equal to very, very, very small. can be arbitrarily small, right? Because you know that it's got converged, so partial sum can be arbitrarily small when x very large. Okay, so we proved that the f and s differ at most 0.1 term, right? So now if I know this, right? So if I can prove this, then I modify to this, then I can prove this. Okay, so this is the first step. Okay, so now we need to start to do a reduction. We need to do a reduction, right? From claim that I start from f. This a q sigma, and the reduction from another fact that I will mention here. Okay, so which is this. Okay, well, we want to make the assumption on this guy and try to make this. Okay, so let's try to do this. Okay, so let's consider this FAQ. Write this. Let me just write results. P. Okay, so this is 1 over P sigma 1 over 5Q, and then with this, right? So this is the inner product. This is the group representation results that you take a chi and then you sum over chi. So this guy will be 1. Okay, so compared to right, so this 1 over P A mod Q 1 over P to the S. So when you take S to be real, you get 1 over P sigma. And so this is just 1, right? This guy is just 1. So it's stupid, but just write something. Just write this. Okay, so this guy will be 1. Okay. So now you separate into 2 terms, 1 over 5Q, and the summation of all chi of A bar, and the summation P, chi of P to the sigma, which is 1 over 5Q, summation chi of A bar, F chi of sigma. Okay. So now we do partial, right? Because you can check that this guy absolute converge, right? So they can exchange. Okay, so finally we get this function, right? So this f chi of sigma will be summation of chi of p to s, sorry, p to a sigma. Okay, and sum over p. Okay, now this looks like the L function, right? Because L function is a product. Okay, so finally we can reduce the problem to the L function. Reduce a problem to the L function. L chi of s will be x chi of n to s. Okay, then there's a L function product p 1 over chi of p by p inverse. Okay, s. Okay, so this is the Euler product. Okay, so finally let's take log. So we can take log of L chi of s. Okay, so simple calculation, right? This is sum. You get 1 minus chi of p to s. Okay, and okay, so this is summation p, summation m from 1 to infinity, like chi of p to the m, p to ms 1 over m, which is let's call it chi of s, right? So this is the m equals to 1 term. Bad notation. So this is p to ms divided by m, right? So when m equals to m equals to 1, then you get first term, and then also second term, which is the higher order term. Okay, so this is the m equals to 1 and m greater than 1. Okay, so now we already get a reduction like this, right? Okay, so now let's consider this. Let's consider a higher order term. So higher order term can be easily computed, right? It can be easily bounded. This is similar as a Riemann zeta function. So look at this, bounded by this, right? Because the character is modulo 1. Okay, so this m from 2 to infinity, mp to sigma. Okay, so you can write it as summation p, summation m from 2 to infinity, 1 over mp to the. Okay, because sigma is greater than 1, that's right. That's your sigma is greater than 1. Okay, so this is summation p 1 over p squared, right? Okay, because there's an m, right? So you replace this by p squared, which is converged. Okay. So this guy is bounded. This guy is bounded. Okay, so it looks like we already get an answer, right? We are very close to the results. right? The reason is this, right? Because if this is true, right? Now this is true, so I can write all the equation as this guy. I can write f chi of x s, right, is log lx chi up to the O1 constant, up to O1, right, as a sigma greater than 1. Okay, so now this f chi s is the same as is contribute from this L function, right? So if I want to say now this guy is written as this guy, right? So now if I know the arrow, or I know the magnitude of this log L, then I can go back to bound the list. I can go back to know the FAQ. Okay, and then we may have a chance to prove that this FAQ actually look like this one. Then we get our results. Okay, so this is the difficult part, the final part. Okay. So our goal is to find the contribution, right? So we need to find the contribution for different characters. Probably this is the difficult one. Okay. Okay, so if chi is a trivial character, then this is simple, right? Because L chi of chi 0 is already bounded. This is the results that we just proved. That's this one, right? Plus some error term. Okay, so this is still due to the partial summation. So I don't have to do anything, then I can prove this. Okay, then you just take L of s chi 0. Okay, and the very simple calculation will give you log of sigma minus 1. Right? Because take a log of this is constant, right? So we plug some O1. Okay, it looks like we proved the results, right? Because this guy already contribute a term which is show up in the FAQ, right? So this guy already give you a result. Okay, okay. So this this function, right? This function. So this will give you something. This will give you that right. This will give you your f chi 0 s is already log 1 over sigma minus 1 plus big O1. Okay. Okay. So and this is true for, let's say, sigma greater than 1. Okay. Okay. So this is the contribution of the trivial character. So let's consider the contribution for the non-trivial character. Okay, so so this is hard part. Okay, the fact is what? The fact is that I already know that the partial sum of the non-trivial character. I already know the partial sum with the non-trivial character is bounded. Okay, so it's big O1. Okay, so which tell me that I should be very happy to say that when I should be very happy to say that our L chi of S is analytic. Okay, so I mean I want to take a log. I want to take a log of this. Okay, so let's assume a lemma. So that this is lemma that's very difficult, and we will prove in the next videos. I will spend a lot of time to prove this. Lemma is this: L chi of x is non-zero. So I should L chi of s is non-zero. Okay. For chi is not chi is not principal. So I should say s is 1. Okay. So this is our lemma. So if your non-principal character in your L function at s equals to 1 will not be 0. I know it's analytic, right? But I don't know whether it's 0 or not, right? Because if it's 0, then I take a log, it will cause a problem. So this lemma tell you that you don't need to worry. Okay, so this guy is bounded. Okay, then we prove our theorem done, right? Okay, the reason is that if log L chi of s is bounded, then we go back to this. Theorem, right? Then this FA of Q, the contribution term which is unbounded only comes from the chi equals to trivial character. So when chi is trivial, that you get the first term 1/5 q of log. And maybe let me just write down. Okay. Okay. So now our AQ sigma have the contribution from log L principal character of S plus log L principal character of non-principal character of S. Okay. And up to the O1 constant. And then these guys I already proved, right? So this is what we already proved in the using the bound, the property of Dirichlet character. That this is I already say that the log of the principal character of L function is written as this form. And also, but these terms by a lemma that I say these guys are analytic by the summatory function, the partial sum. And I also say that when S approach to 1, that these guys do not blows up, right? These guys are non-zero. Okay, so log is finite. Okay, so these guys are always finite for every q, right? Because you at most get the finite character for finite group. Okay, then we prove FL of q sigma is looks like 1/5q to 1/sigma minus 1 form. Now, yeah, so proof is done, right? Because we prove this, and by this lemma that we prove SAQ. Okay, so this is a very hard reduction that these guys finally go to the L function. Okay, so I control the function L, I control the bound of L function, and I go back to F chi of S, and I go back to FAQ, and I go back to original theorem. And once we prove this, we prove that they're infinite prime, the infinite primes of A mod Q. Okay, so this is a very difficult theorem and very amazing that you learn a lot of number theory, try to prove this. Okay, so see you guys next video. And the next video, okay, so the next video, what we do, next video is that we want to prove. Okay, so next video, next or final one. The final is that we want to prove that L chi of 1 is not 0 or a non-trivial character. Okay, so see you guys next videos.